So in the first video related to this pre-lab, we talked about setting up the data and packages, and then a little bit of a review of summary statistics and data visualization for one quantitative variable. And now we're going to talk specifically about the bootstrap. So the bootstrap is this procedure where you're going to pick yourself up by your bootstraps to create a sampling distribution when you can't go back and take repeated samples from a population. So what we're going to do is we're going to resample from our existing sample, and we're going to use those called bootstrap samples to generate some sample statistics and allow us to create a sampling distribution. So the function that's going to allow us to do this is the resample function, and what that does is it's going to take samples with replacement, and that means sometimes we'll get many copies of the same observation, which in this case is a person, and sometimes we won't capture a particular person at all. If we just run resample by itself, it doesn't really do anything, so I could either hit the play button or Control-Enter on this line, and nothing prints out. And that's because you sort of need to tell Resample how many times to do the resampling. So let's try just doing it once. So I'm going to do one time the activity of resampling my GSS data. And I'm going to assign that using the assignment operator, which is that little arrow. It's like a less than sign and a dash. I'm going to assign that into the name bootstrap sample. So if I Control-Enter on that line, now I get a new object in my environment. So let's look at this object. And it's an interesting object because it has 2,348 observations, so it's the same number of observations as my GSS dataset, but it has 48 variables, so it has 3 more variables than my original dataset. Let's click on it and look at it. So just like the original dataset, which is GSS, the first variable is respondent ID number, and then I've got number of children, age of respondent. So in my bootstrap sample, I still have those same variables. But you can see that respondent ID number doesn't go 1, 2, 3, 4, 5. Mine starts at 1,911, 1,982, and then 98. Yours is going to be different because of randomness, but it will also be not just the numbers 1, 2, 3. So that's showing us which of the observations got sampled into our bootstrap sample. And then we could scroll over to the side, all the way over, and we can see that there's a few different new variables that got added on here. So we've got orig ID, so that's the row number again, and then .row, this is the row number for my new bootstrap sample, and then index, this one is just going to be 1 because we've only taken one bootstrap sample. Let's scroll back over to the other side. I'm going to use the little arrows to sort by respondent ID number in my bootstrap sample, just so that I can see which observations I got in here. So it looks like I got 2 copies of the second row, I got 2 copies of the third row. I didn't get the first person, I didn't get the 4th or 5th person, but I did get the 6th person, I got that 7th person 3 times, I got the 8th person twice, etc. And again, your bootstrap sample is going to be slightly different than mine, so you're not going to see those exact same numbers. So it has the same number of observations as our original data set and the same number of variables plus 3 more to help keep track of things as we do more samples. And we could make a histogram of the highest year of school completed variable in this bootstrap sample. So again, you could pause the video to try and figure out how to make that histogram. I'm just going to do it. So it's gf underscore histogram, parentheses, and then tilde, and the variable is named the same thing in my bootstrap sample. It's highest year of school completed with underscores, comma, data equal to, and now I'm not going to say GSS, I'm going to say boot strap underscore sample, because I want to pull it from that different data set. And if I control enter here, now I get my histogram of the Bootstrap sample. And I could flip back and forth to look at the histogram from my original data set and the histogram from my Bootstrap sample. And the question is, does that look similar to the distribution of the original data, and what's different? So I would say it looks very similar, but slightly different, because it's a random sample with replacement from the original. I might go and adjust my bin width so it's a little bit easier to see. So I'm going to scroll up back to my original histogram, and then I'm going to add in the bin width option, and I think I'm going to say 2. So let's try Control Enter. So that's a little bit easier to see the shape of the distribution. So that was my original data from the real GSS dataset. Now I'm going to scroll down and I'm going to find my histogram from the Bootstrap sample, and I'm going to put the bin width argument in here as well. Bin width is equal to 2, and Control Enter. So now let's flip back and forth. Still very subtle, I think, here. Not very much of a difference between these two distributions, but you can see that there are some subtle differences. And then the other question is, does your histogram of a Bootstrap sample look exactly the same as mine? And I'm certain that the answer is no, it doesn't, because it's a different random sample. So that makes sense. And this brings us to the next issue, which is the issue of randomness in R. So R is really good at taking random samples, or pseudo-random samples technically, and these Bootstrap samples being random is good, because then they're kind of like random samples from the population. But it can be really frustrating to do things with randomness in R, because when you knit your document, the results change. So every time that you run a line of code that has some randomness in it, like if I went up and reran this line of code and then made my histogram again, it would be different than the previous one. And when you knit your document, it runs through, R runs through and runs every piece of code, and so it will get a different random sample every time. So that can be frustrating if you're trying to write sentences about things that you have found. So the way to fix that is to set the seed for the randomness, and we're going to use this set.seed function. And set.seed takes an argument which is just a number, and you can put your favorite number in there. So I often use 42 because that's the answer to life, the universe, and everything. I also sometimes use the date, so like 03/19/2020. It doesn't matter what you pick. You can use your birthday, whatever you want. So if you Control Enter on that line, nothing happens in your console, but now we've set the pseudo-random number generator in R so that it will always start off at the same point, and your quote-unquote randomness will be predictable. It'll always sort of follow a predictable pattern. So if I set the seed and then take a Bootstrap sample and do the histogram of that Bootstrap sample, and then take another Bootstrap sample and do the histogram of that Bootstrap sample, these two will be different. So I can click back and forth, and they're slightly different. And then if I set the seed again and did a Bootstrap sample and did the histogram again, now this histogram, it's not going to be the same as the one immediately previous, but it will be the same as the one before that. So it always brings you back to the same point in the randomness. Taking just one Bootstrap sample isn't that interesting. If we're going to make an interval, we're going to need to repeat the Bootstrap sampling process many times, and many usually means at least 1,000 times. And we don't want to store 1,000 full data sets that have, 2,348 observations of however many variables it was, 45 or 48 variables. So we're going to stick the resample command inside a summary statistic function. So I'll show you what that looks like. So here I have my do, but I'm going to do it 1,000 times. And what I'm going to do 1,000 times is I'm going to take the mean of the highest year of school completed variable, but the data is going to be a resampled version of GSS. So it's going to do that whole process 1,000 times. It'll take a sample with replacement from the original data. It'll be the exact same size. It'll find the mean of the highest year of school completed variable in that Bootstrap sample, and it'll repeat that until it's done it 1,000 times, and it'll assign the result of that into an object called boot. So let's Control Enter there. And this could take a little while to run because it has to do it 1,000 times, but it should finish. And now you have even one more thing in your environment. And the thing in your environment is shaped differently than the first two objects that we had. This has 1,000 observations of one variable. So let's click on it and look at it. So what this data set has in it is a bunch of means. So it took a Bootstrap sample of size 2348, it computed the mean of the highest year of school completed, and it put that mean in here. And then it did the same thing for another sample of size 2348, and another sample of 2348, and on and on. It did that 1,000 times. So now what I have is a bunch of means. So it has 1,000 observations, which correspond to the 1,000 Bootstrap samples, and just one variable, which is the Bootstrap statistic, and I'll put in parentheses mean, because we did a mean here. So then we might want to look at the distribution of that statistic. So again, we could make a histogram of that variable mean inside the data called boot. And if I Control Enter here, does this look like our original histograms? Well, no. It looks very different. And that's because it's not the distribution of a sample or a Bootstrap sample. It's a distribution of many Bootstrap statistics, and I'll put in parentheses means. So one observation in this histogram is not a person, it's a mean of a Bootstrap sample. So it's a little bit abstract. And then the question is, what is the mean of this distribution? Where is this centered? So you could think about how you would do this. You could pause the video and then see if you were right. And I'm going to do it. So I'm going to take the mean, parentheses, and then I need a tilde. Oops. I need a tilde. And then I need the name of the variable that I want to take the mean of. And weirdly, the name of our variable is also mean, but then I'm going to say comma data equals, and then the name of the data set that we're trying to pull from, which is boot. And then I could Control Enter, and the mean of this distribution is centered at 13.7. So does that make sense? Yes, because a Bootstrap distribution is always centered around the original sample statistic. So we had seen the original sample statistic was 13.7, and so we would expect that this distribution would be centered around 13.7. So now that we have a Bootstrap distribution, we might want to create an interval. Rather than just having to give a point estimate, we'd want an interval. One thing we could do is just use the 95% rule to kind of eyeball what the middle of that distribution is. And my guess would be, 13.65 to 13.85. but we really want to be more precise than that. And the confint function is going to help us do that. So if we run confint, short for confidence interval, of boot, then we're going to get this output, which has the name of the variable. It's got the lower bound of the interval. It has the upper bound of the interval. It tells us the confidence level, the method by which the interval was determined, and then it has the estimate. So that's the middle of the interval. So the way that I would interpret this output is by making a sentence about my confidence interval, and I would say we are 95% confident that the true mean of a number of years of school for Americans is between 13.6 and 13.85 years. So the Bootstrap is allowing us to pretend like we were able to take repeated samples from the population by bootstrapping from the one sample that we actually had. And one thing that can allow us to do is to create a confidence interval.